Okay, so welcome back. And so now the last thing that we're going to talk about for this series of topics is going to be the surface area that's generated by revolving a parametric curve around an axis. Okay, so I'm going to do the x-axis, but again, there's a similar type of problem for the revolving around the y-axis. And so I'm going to start with what we did last time, where we're dealing with non-parametric, where we're just dealing with regular functions, right? So in that case, we had this formula, right? This is what we used for finding the area of a surface of revolution, right? And this one is revolved around the x-axis. So we took, remember, we're taking the curve, the arc length of the curve, right? And we're rotating it around the x-axis. So we're taking that curve, that arc length, and we're tracing its path, right? And it's creating a surface of rotation, okay, or a surface of revolution. And so how do we figure out the surface area? We took small disks, right? We took disks by one revolution of a point and used the circumference, right? So we used the circumference of the circle, right? So we took a point on the graph, right? And we rotate it around and we find the circumference of that circle. And how do we find the circumference of the circle? It's 2 pi times the radius. What was the radius? The height of the rectangle, which would be by f of x, right? So this represents the arc. Well, then this is the arc length, right? So we're taking the arc length and we're taking that and we're multiplying it by the circumference of a circle, right? The distance around, and we're taking these little circumferences and we're stacking them from A to B, and that gives us our area. So this integration gives us there. So this is circumference, right? So we're taking 2 pi r, and then this is the arc length, right? And then we're integrating it from A to B to give us the area of the surface. So now, what if we have our curve defined parametrically? Well, then if we have parametric equations, x equals x of t and y equals y of t, then we can do an analogous derivation by saying, well, s is equal to 2 pi times, instead of f of x, we're doing y of t, right? The height, the radius is going to be y of t. And then, of course, this is our formula for the arc length of the curve when we're dealing with parametric equations. So this is what we're going to use to find the surface, the area of the surface generated by a parametric curve when it's rotated around the x-axis. Okay? And again, this is provided that this is non-negative. That this is non-negative over the closed interval. Okay? So now let's do an example.